Our guest speaker is Professor Rob Evans. He is the head of the Department of Electrical and Electronic Engineering. I assume most of you know him, and I would like to thank Professor Rob Evans for accepting our invitation to come here and share his experience and guide us in our future career prospects. To give a brief introduction. Professor Rob Evans is a laureate professor in this Department of Electrical and Electronic Engineering, and his regard has ranged across many areas, including theory and applications in industrial control, radar systems, signal processing, and telecommunications. Professor Evans is a fellow of the Australian Academy of Science, a fellow of the Institute of Engineers Australia, and also a fellow of the Institute of Electrical and Electronic Engineering, IEEE. In addition to this, he has experience of a wide range of industries, and he worked in several universities. So I believe today we will all get to know some secrets from him, how he moved over different phases in his life, and also we can get some tips on how to move if you decide to go into academia. Without a further delay, I would like to invite Professor Rob Evans to share his experience with us. Thank you.
Okay, thanks. So for the next 45 minutes or so, and I'm happy to take questions as we go along, I'll do what I was told and tell you a bit about my career in electrical and electronic engineering. I was born in 1947, a long time ago, and you probably all come across my son, Jamie, who's head of electrical engineering. My name's So let me start. I'll give you a bit of an overview of my career, which really starting with undergraduate at Melbourne University in this department, before this building was built, by the way, in the mid-1960s, and then I was a young engineer with the Australian Air Force. Then I did a PhD and postdocs. Then I worked at the University of Newcastle for 20 years, and I've been back to Melbourne for the last more than 20 years. And then just some observations that there's lots of things you can say as you get older about a career in different aspects of electrical engineering. When I was a kid, I did a lot of electronics, and I started doing it before you could buy transistors. So it was a long time ago. Everything was done with valves, but you learn a lot about electricity, and a lot of things don't change. So here's a career overview, and then I'll get into some bits and pieces for you. So in 1966, I started electrical engineering in this department, and I did electrical engineering undergraduate degree, which was a 4-year degree, and I'll tell you a bit about that. Then, from the middle of that till 1974, I was an engineering officer in the Air Force, working on radar and a whole lot of other things, and I'll tell you about that. Then, overlapping with that, I did a PhD, a master's and a PhD. Then I went to MIT in Cambridge. Then I came back to Newcastle and was an academic, and I was the head of a department in that department in 1985, so a long time ago. Then I moved back to Melbourne for family reasons, and again I was head of department in the early 1990s, and I'm doing it again now. So. And throughout that whole period, I've done a lot of work with industry, and had a few companies, and run a university company, and done a bunch of things. So, an undergraduate at Melbourne University in the 1960s, and I went through exactly the same class as Rod Tucker, who's also a professor here, who's just retired. And so it was a different degree. It was a regular 4-year engineering degree, and it was different times. So the classes were small. There were typically, I think, about 30 students in our cohort going through, and you had to pass year by year. So you had to do all the subjects in a year, and if you didn't pass them all, you had to repeat the year or part of the year, but you couldn't move forward to the next year. So at that time, only 8% of students got through the 4 years in the time of 4 years. half the students failed first year, just left. So it was quite a savage business. There were 20 lectures a week, about 18 to 20, and 12 hours labs. So most afternoons you had to do labs from 2 to 5 and lectures from 9 till 1 every day. And the first 2 years were, the first year was common across all engineering, and the first 2 years were nearly common. And the electrical engineering degree, in third year we were still doing courses in fluid mechanics, thermodynamics, materials, etc. So there was a lot across all of engineering, so we learned a lot of different things. As I say, electrical engineering has grown a lot, there's a lot more material in it than there was, so this was much more focused on fundamentals. There was lots of design work, because most engineers then went out and worked for the telecommunications or the power authority, and you did lots of design. So we had lots of practice doing designs through the 4 years. You had to do industry work in the break. We also had a professor at the time who's from this university, and you're here, so Charles Morehouse was a famous professor from here in the power systems area, and he also made us do something called discussion sessions where we had to read literature and go down the art gallery and look at paintings. And so we all took it as a bit of a joke, but when you look back on it, it's actually really valuable to, because this was the idea that engineers weren't cultured enough, so we had to be sort of gentrified. You had a choice about mathematics, and so I did 4 years of maths straight through, as well as the engineering. And in the final year, for example, a third of it was mathematics, and the other 2/3 roughly were electrical engineering. And it was very intense. There were hundreds of lectures in electrical engineering part. And we also did 4 small specialisations of 15 lectures each or something in four specialist areas. But everyone did a huge common electrical engineering subject with labs in final year 2. So everyone learnt a lot about machines, about microwaves, about electronics. So it was a totally different structure. The structure that you have now is much more like the US style systems that were in units, and you can build your own path through units. This was much more disciplined. You didn't have choices. You just had to do all this, and the only choice at all was that did you want to do mathematics or business in final year, and which of the specialisations did you want to do? There were about 8, and you could pick 4. That's it. So that was what the undergraduate program was like. It was very intense. We learned a lot, and it was a course that suited the times, and there was a small cohort of 30 or so students who went right through that program. So now this should go click. Yeah. So then I in the middle of that, as an undergraduate, I actually joined the Australian Air Force to get a scholarship, and I was interested in some of the things anyway. So that's me as an Air Force officer. So as well as doing that, I learned about leadership and management, and I went to the Air Force training. And when I finished, there was a very extensive training in the Air Force about how to be an engineer in the Air Force, and also how to lead. So when I was 22, I had 25 people working for me. So that happened very quickly, and you got taught a lot about leadership and management in this big structure. And so I had a lot of responsibilities. And so I worked mainly in radar systems, and it was quite interesting. In fact, it was highly innovative, and a lot of that was up in Williamtown, north of Newcastle, which is how I ended up at Newcastle. But and it's a radar very similar to this one that I worked on. Inside that is a radar that allows you to measure range and bearing and the height of objects. It's quite a fancy radar. So let me tell you what was the technology at that time. So in 1969, the technology we had there on these displays, the technology allowed us to, it was all run from 2 computers called Marconi Myriad computers. They were big as that desk roughly, and they were fed by paper tape. So you typed things on paper tape, fed it into a paper tape reader and we loaded the programs in that way. Now, the computer had 8 kilobytes of memory. So there were two of them with 8 kilobytes of memory. The memory was magnetic core, little cores of ferrite with a coil through them. So you set the flux one way or the other to remember 1 or 0. All of the gates in that computer were resistor-transistor logic, so individual transistors with resistors on them. You could see them all the gates, and there weren't many. And the computer, so the operating system was 80 bytes long. And let me tell you what, and it had a clock of 1 megahertz clock, right? So now you've got on your phone a 2 gig clock in your computer. It's got 128 gigs of memory. This had 8 kilobytes. But there were two of them with 8 kilobytes. You can't even enter your password without about 2 megabytes on the current computer. This had 8 kilobytes. And it had a store, a backing store, with 64 kilobytes of memory. So we wrote the programs, and a program would, a bit of it would be downloaded, run in the 8 kilobytes, finish that part of it halfway through, put away, and then the next bit of the program would be downloaded out to 64 kilobytes. Okay. So what did this computer do? So in 1969, we had colour graphic displays. So there was the radar data being, as the radar span around, it came down through microwave links, went into some fairly fast logic, but it was all slow compared to today. And the interface went into these computers, and then it got drawn up on displays. So there was that. Then there were alphanumeric displays generated by the 8 kilobytes in these computers, so you could actually see, and you could track targets, so you could follow things, so there's quite a lot of processing going on. And you could have, we had a mouse, so there were 16 displays, they all had mouse in 1969, right? And so you could go and click on a target, you had a pull-down menu, and it was colour graphic, mixed writing display, and analog rotating radar display. That was all in 1969. And so, all running in 8 kilobytes on a 1 megahertz clock with real-time data from 2 radars. So today, you just wouldn't dream of being able to do exactly the same stuff without 256 gigabytes of RAM and God knows, 10 computers all with 4 gig clocks, or it's just amazing what was done in those days with very simple, crude stuff. And so a lot of that technology didn't catch up and get back into consumer use until the 1990s. And so these were just specially built for different applications and for air traffic control. This was an air traffic control type thing, controlling fighter aircraft. And the whole thing was quite an amazing experience that from what I'd learnt in undergraduate in 1969, we built a little computer out of transistors in the lab here. It's one of the projects we had to actually build a full computer, because computers were only just sort of around, just getting started. And so we built a full, simple computer in the lab. It was one of the projects we did. But then to see, and when you get to see it working in this application and you're so intimately involved with what's going on, because these things used to break down, so you had a lot of chance to get in and put crows in there and find out what was going on, find out how things work, make modifications. And the radar electronics is a fascinating area, a mix of RF and digital stuff, very sophisticated. So inside that radar there were 20 racks of electronics, each this high, this wide, double-sided, just full of boards of electronics. And that's typically what you see in a big radar system. So all that, some of that was digital, some of it was analog, a lot of it needed adjusting and tuning. Very interesting stuff. Mostly no digital filters. You couldn't go fast enough to do digital filters, so it's all analog. But I just learned so much from that experience, and it was so far ahead of what was going on out in the commercial world that it was a huge huge opportunity for me. And so one of the lessons I took away from that was if you can get involved in an exciting leading edge project and you really dive into it, you learn so much for the rest of your life. So there's still things I learned from spending 5 years there that I still draw on now, lots and lots of things. Apart from the fact that, you know, you might not want to go into the military, and I don't recommend you do, but the thing is I did learn a lot about leadership and management and organisation because I got trained to death. They endlessly trained me in different things. But as well as this technical experience, which was phenomenal. So, and at the similar time to that, I did a PhD, basically in mathematics. It was a very advanced PhD in an area called function space optimization. So and it was all inspired by signal processing that I'd seen in radars. And I did work on adaptive signal processing very early on in those days. And I did some work on data communications and antennas. So while I was doing my PhD, I published a bunch of papers in IEEE, some on some antenna theory, some on some communications theory, some on optimization, and some on radars. And that's Newcastle University where I did that. And there was a small group at Newcastle University at the time. I'd never heard of them. When I left here, I wanted to stay here and do a PhD. And the Air Force wouldn't let me. I said, no, you have to be posted. I was upset. And when I got there, I went and found out there was a university at Newcastle, which had just opened in 1970. So it was roughly exactly the same time as I arrived. And it was headed by a guy called Brian Anderson, who'd come from Stanford and just done a PhD with a guy called Bob Newcomb. But this was the group that was just all learning about. Rudolph Kalman was there, Tom Kylis, really great people were there at Stanford at the time, and it was a real hotbed of learning. And he brought that whole culture back to Australia. And he was a full professor at 25 years old. He was a fellow of the IEEE by the time he was 30. And he became president of the Australian Academy of Science. And Brian became the top engineer in Australia. And he's still a very close friend of mine. He's in his mid-70s now. And so it turned out that Brian had created a group here of all these hot shots from MIT in different places around the world. And I was just stumbled across this by accident, pure accident. I was actually really upset, and I sent a formal complaint to the Air Force saying, why didn't you let me do a PhD? I'm so glad that I didn't, because I did one up there with these stars, and it was amazing. So a very small group, half a dozen people, a really interesting experience. And so out of that, I went to MIT, and then I went to Cambridge University, did postdocs there, and worked on areas, stochastic control, information theory, signal design, lots of stuff, and spent a lot of time just reading everything I could get hold of in all sorts of areas, and meeting lots of people who later became famous all around the world. So, if you do a PhD, the story is make sure, the only thing that matters is getting a good supervisor. So if you're thinking about doing a PhD, not about the topic, it's about trying to find someone who is famous, powerful, highly energetic, a great achiever, that sort of thing, because they network you into the rest of the world, and you get rocketed up if you get the right supervisor. So it's critical that supervision is what it's all about, get the right supervisor. Someone who's well known around the world and who's highly respected gives you an enormous step up. And then if you get a chance to do a postdoc, do it. And try and find a postdoc that allows you to have a lot of freedom, work on really exciting things, and go to the best place you can get to. Just because, you know, Melbourne's a really good place. It's a really good university and it's ranking very high in the world. But MIT, Cambridge, Stanford, Oxford, those places are absolutely special. They're different, they're special. So if you get a chance to go to them, even for a short time, you should do it because they're amazing. And there's a great history in those places. And so most of the electrical engineering you learn today, which I'll show you later, was generated out of MIT in the 1930s. That's where it came from. All so the way you use Fourier transforms, the way you do Fourier transforms, the way you do signal processing, all the types of analysis, the way you do digital stuff, the comms, all came out of a group at MIT. And that's the group I worked with when I went to MIT. And read. So when you do engineering, you tend to, you know about mathematics and physics in some sense, but it tends to be a pragmatic view of it, but you probably don't know much about philosophy, and sometime in your life you discover philosophy. So you should, when you get a chance in these periods of a PhD, postdoc, or if you don't do that path and do other things in your life, try and get into all this other stuff, because there's a phenomenally interesting world of stuff that bears directly back on your ability to do good engineering. And I consider myself an electrical engineer, not an academic. And you'll see in a minute, I've spent most of my academic life doing real engineering with companies. And in fact, running the university commercialisation company in Newcastle. Anyway, so that's PhD and postdoc. So then, when I came back from overseas, I went to University of Newcastle, and I was a young academic. And I started a little company that I did consulting work from, called Australian Systems Research, and I used that with a few other academics. We did a lot of work. In 1982, for that 10-year period, I ran the University Industrial Electronics Commercialisation Company for the university. I was also head of department for a long period of that, and I had a cooperative research, an ARC cooperative research centre in industrial control with my good friend and colleague Graham Goodman. So we won that in 1988, not 1888, 1988. I probably look old enough to be, that's probably right actually. And so what sort of research did we do? Well, we did all sorts of research. I tried to do theoretical research. I like mathematics and I like doing theory, so I did a lot of work in optimisation, kept publishing there. But I also am an engineer, and I was trained as an engineer, and as a kid I loved doing electronics. So I did a lot of work in power electronics, and we built some variable speed AC drives that were just starting in the mid-1980s for Hawker Siddeley. And you know, the story with electric motors is really interesting. There are 6 electric motors for every person on the planet. Like in a country like this, 20 million people, there's probably 200 million or more electric motors. And in any household, you'll find there's a fridge and the air conditioner, and you just keep going. And in your car, there's many motors, etc. And there's millions of microprocessors, but in your washing machine, in your dryer, just on and on. There's motors everywhere. So when power electronics, when electronics got to the point that you could actually do switching electronics fast enough and, you know, in a reasonable way and small enough to control motors started getting, AC and DC motors started getting bits of electronics stuck on them. And it's an absolutely huge industry that you don't sort of hear about. So the design of electronics, power electronics, industrial electronics, that associated with motors having variable speed, driving things around, doing things, is a huge and interesting industry. So we got involved in that in a big way. We built a variable speed drive, a 10 horsepower and a 25 horsepower, 25 kilowatt actually drive for this big English company, Prof, and we built switch motor power supplies and lots of things that were all new at the time. We also got into building supervisory, these SCADA systems, supervisory control and data acquisition systems. So when microprocessors started in the mid-1970s, they were not easy to use, and they weren't cheap. You know, but by 1980, you could start getting processors that you could do, single chip processors, you could do reasonable things with. They still only had a 1 megabits clock. And people started embedding them in everything, putting them in washing machines, putting them in everywhere, and they started this business of building monitoring systems. And that's the Northwest Shelf gas pipeline. And one of the projects we did a lot of them, was build a monitoring system along the pipeline. But the idea is you build little boards with processors, sensors, okay, all sorts of sensors on them. And a lot of people think the Internet of Things is new, but in 1982 we built a supervisory monitoring system, a SCADA system, for fire monitoring in Victoria with 1 million monitoring points, using 300 bit per second lines. not the internet, 300 bit per second lines, and it had a response time of 1 second. So that if there was a fire anywhere, it was reported centrally within 1 second. And it was 1 million monitoring stations. We did one on the northwest shelf gas pipeline that was being built then, on huge lengths of pipeline monitoring for leaks and pressure and other things. We did just lots of them. Around the country, they were real industrial jobs with industrial partners. And so this whole business of computer-connected monitoring became a huge business around the world. And some of them were wireless links. So you just had a processor monitored, solar powered or powered plugged in somewhere, monitoring 20 or 30 things. Another one 200 metres away doing the same, another one, and then messages were just being passed wirelessly along these things, all by wire, and all being controlled centrally somewhere. So the world suddenly got monitored because of the ability of processors and cheaper sensors. Now the Internet of Things today, which is sort of the big thing, of course, is there's an internet around. So the networks are all there. You don't have to build special networks. And the processors are smaller and there's more sophisticated sensors. But it's just an elaboration of that. And speaking of the internet, when I was at MIT in the early 1970s, I had a lot of relationships with a group called Bob and Newman, who were MIT professors who'd started this company, which later became Martin Marietta Corporation, or bought by Martin Marietta. But anyway, they were doing all sorts of consultancy work. They're acoustic engineers originally, but they spread out with other things. And they were given the job of building the first internet by the US Army. So they built the first ink processors, these message passing processors. So in early 1970s, all the people who worked at Bolt, Brand and Newman had a teletype, an old teletype, looks like a typewriter, connected with 300 bit per second data rate wires, and they were on the internet. And so they were sending tom@stanford.com in 1972 messages. And they could log on and FTP files out from a computer in San Diego or Washington from their homes in 1972. So that was done then, and it was done in 9 months. They built it in 9 months. So quick it took. So they just had this spec, because what had happened is people, Paul Barron and a bunch of other people had come up with the idea that the US communication system was non-robust to attack by nuclear weapons. That was the problem, and that someone could just take out a bit and the whole network would go down. So they thought, well, why don't we break messages up into packets, have wires everywhere, and the packets just go, and they reassemble at the other end, and then you can take any bits out, but you still find the path. That was what motivated it. And they thought that was a good idea, and so they said, let's fund a demonstrator. And for $1 million, they funded the demonstrator. And Bolt, Brand and Newman built the demonstrator for these universities who were part of the network. It was that simple. It wasn't even considered to be a big deal. So when I was there, people just saying, oh yes. And they decided that probably in order to keep it going, they'd give it away, let everyone have it, not just people in the military. So they did, which is what people often don't understand about the United States military. They fund everything and they let it all go. They let a lot of stuff out the door because they are the great innovation engine behind the US economy. A lot of stuff they just don't keep, they just let everyone have it all the time. And they let everyone have the internet. And then, it became its own life and it got more commercial and various attempts were tried, but then it became this great thing it is. But in the sense, it's just a packet switch network. So fault-tolerant computing, antenna tracking systems. So I did a lot of work on upgrading the Parkes radio telescope, as well as, so all these things we were writing papers on, but we're also doing industrial work. So the lesson there is really, and that's me, in mid-1980s, working on the Australia telescope, which was out at Kogarah. So I was on the team that designed this with the CSIRO and a big consulting engineer group in Sydney, and then the tracking systems we built at Newcastle University, and that's when it was being opened by Bob Hawke in the mid-1980s, and they made us have it so that all the antennas bowed when he came in, so they were all sitting here and they all went like this. Except one of them didn't do it. And it was our fault. But anyway, it was really exciting. And I used to go up there once a week for about 18 months working on this system. It's very exciting and really interesting stuff. All just to do measurements of the, outer space, of course, but really interesting stuff to work on. And we also built and commercialised a satellite tracking system, because all of this was happening because you had microprocessors you could put in little boxes and you could do things. They weren't big computer systems. So we built some microprocessor satellite tracking systems which got stuck on tracking system all over the world. In Antarctica, in fact, we had 6 go to Kazakhstan, to the Russian space launch facility for doing their tracking of things going up, and that was technology that came out of our group. So that was really great fun. It was hard work, really great fun, and we learned a lot about real control systems doing this, and people all around the world were wanting us to publish more and more on it, and we just, after you do an industrial job like that, you get so sick of working on it, you can't be bothered writing it up and publishing it, which is another interesting phenomenon. So then I came back to Melbourne in 1992, and I said I had a cooperative research centre in signal processing until 2002. So for 10 years we had a lot of fun, and then in the department then we had 2 cooperative research centres. Rod Tucker, who I'd gone to university with in the 60s, had come back from Bell Labs in the US, and I came back down from Newcastle, and he had a CRC in photonics, and I had one in signal processing. And that was a big thing we did in the department. And I was head of electrical engineering then. 2002, I became director of this National ICT Australia thing, which I did for 10 years. I was dean of engineering in 2007 during a restructure, and I'm head again back now. And over this period, I've had lots of PhD students. In fact, from 1980 to now, I've had 80 PhD students that have graduated. And I've had raised a lot of research money into this department, a couple of $100 million through NICTA and CRCs and other things. It's all been for everyone's general benefit. And as you get older, you get lots of responsibilities. So I've done lots of leadership roles in the Academy of Science, the Engineering Academy, the International Federation of Automatic Control, the ARC. There's lots of different things. So, things accumulate over your life, doing a mix of research and industry engagements and leadership roles, and you just end up with this big pile at the end. But so at Melbourne University, what sort of work have I been doing in the last 20 years? Well, I've been working on radar. I'm still real interested in radar from my Air Force days. So we do a lot of work on tracking, and a lot of our trackers now are used around the world in radars everywhere. We did some new, very innovative work on waveform design, because a radar is basically a big antenna that sends out waveforms that bounce off things, and when they come back, you're trying to figure out as much as you can about the object out there, how far it is away, where it was, what its shape was, what its speed was, whatever you can figure out. And it's often mixed up in clutter. So like other objects nearby or clouds or God knows what. So the secret to radar is really about this waveform design. And the big innovations in radar over the last 100 years have been about clever ways to design waveforms. And so we started looking at things when a waveform comes back, you actually change the waveform next time based on what you've learned this time. So you adapt the waveforms 1,000 times a second, really quickly. You're endlessly adapting the waveform to learn more and more about the target in the best way. And so that was one of the big innovations that came out of here that we did. And then in the last 7 years or so, we've been working on a tiny little radar with Stan Skafidis, who was one of my PhD students in control theory. We've been building a radar up at 76 gigahertz, very high frequency, a tiny little radar. And that little chip there, there's a dollar, that little chip there sitting on a board, that's an antenna, a receiving array, that's a transmitting array. That little chip contains 2 transmitter, complete transmit chains, and 8 receiver chains at 76 gig, and the chip measures 5mm by 5mm. It's on CMOS. So that was something that we built here. That's a little working time. That's the picture of the. So on there, there's hundreds of amplifiers, and you can't see it on there, but there's about 40 or 50, more than that, nearly 100 coils and transformers up at 76 gigahertz integrated into that little package. Probably the wrong lecture. So this is something really exciting we've been doing, and we want to get this commercialised. So the use of this is that we can package all that up into a radar about the size of the end of your thumb, weighs nothing, works over a few hundred metres. It gives accuracies of a few centimetres and about a metre per second in speed, a few centimetres in range, and a degree or so in azimuth, in elevation. We can put all that in a thing. It costs just $10, because instead of costing $1 million or $50 million like a big radar does up at these frequencies, because it's all CMOS, everything's integrated onto one tiny chip. It costs nothing. CMOS costs 6 cents per square millimetre in manufacture. So if you can manufacture large quantities, it costs nothing. So where are these going to go? Well, cars want to put 6 or 7 radars around them, and people are trying to get the price of that down, and this is zero cost type option. UAVs, all the little UAVs, people want to put radars all over them to stop collision, but they have to weigh nothing. And this is about the right range. And they use them for getting good landings and collision avoidance and all that. So there's a big market coming in tiny little cheap radars on bicycles, on motorbikes, buses, everywhere. So this is a market we've been trying to get into, and we've spent a lot of money already building that chip. It's quite hard work building a chip like that. And now we're finishing it off and trying to commercialise it. So, and I've done a lot of work in control systems and hybrid systems. In fact, Stan Skafidas, the professor in the department who's a chip designer these days, did his PhD on hybrid systems with me in the mid-1990s in control. Then he set up a company building wireless LAN chips, and that company was set up in Austin, Texas in the US. And he's recently set up another company here doing 5 gigabit per second wireless LAN up at 60 gigahertz. So just down in Bouverie Street, there's a little company of Stan's students building and selling. I think they're building currently 10,000 a month. But they're manufactured in Korea. Building wireless LAN chips, tiny little chip just like that one, size to be able to slot into a phone on the whole packet. 5 gigabit per second over about 20 or 30 metres, 5 gigabit per second wireless LAN running at 60 gig. So it was based, and this is 76 gig now, little radar, 200 metres, similar sort of idea. So a lot of work in systems theory, trying to understand the role. This is theoretical work, the role of information in systems theory. A lot of work on signal processing of all sorts of different types. These are hidden Markov models, multi-arm bandits, a type of stochastic process, stochastic dynamic programming, Bayesian methods, all that sort of stuff. And also, as you get older, you get a bit more interested in some of the other sides of things. And I've been doing quite a lot of work on technology and innovation, the relationship between science, technology, innovation, technology and society. What does it mean to have a technical literate and advanced society? How does it all work? So that's a really interesting business too. And I've had a few PhD students. And one of them, Rihanna Mohadeen, has just finished her PhD on the impact of small power systems on the lives of women in the developing world. So she spends a lot of time in the Philippines and up in northern India and different places, looking at the impact of technologies. And it's amazing, just by a little tiny bit of extra power, the lives of women in those places can be improved tremendously, just massive improvement in quality of life. And so we've been looking at those issues a lot, and designing things, looking at a lot of different things, and using engineering skills to achieve something new. So some observations. My observations are, when you're studying, learn to understand things properly. And that might sound simple, but it's actually the key. It's actually the key. So what it means is when you're learning about bus transforms, circuit theory, or digital comms or something, just keep battling away, thinking about it, till you really, really, really understand the idea. And what you're trying to train in yourself is the ability to know when you understand something. To actually know when you've gotten to the bottom of it and you really understand it. So you can ask, people can ask you anything about it and you understand it deeply, so you can sort of see all aspects of it. And that's different to sort of a shallow understanding where you learn something out of the book and you sort of get it and you can sort of answer questions on the exam. But you have to learn the skill inside you that you finally know, I really understand this. And if you take examples, I've taken examples in my life where it's taken me 40 years to understand a simple idea. And I finally get it. I finally, after reading it over and over again, and I've done exams on it, I've written papers with it, I didn't understand it. I finally get it really quickly. I've understood it. I know I've understood it. So over time, you get this skill to learn when you finally really understand something. And the only way is to really battle with something, think about it a lot, try and use it till you really understand. So that's a really important thing in life. It also is very true that you need to understand the fundamentals, because in the end you apply them everywhere. Understanding what engineering is about and doing real design. So you don't often learn it. Engineering courses belt you through starting learning all these details, but what it means is when you're doing engineering design, it's a serious responsibility. If you're going to build a building, you have to put your hand on your heart and say, I've done all these calculations, these simulations, I can promise you it's not going to fall down. And you absolutely know it's not going to fall down. You know it. You've been able to prove it in a whole range of ways. When you design a bit of electronics for a company, and I've done this many times, where they're going to make 5 million of them, you cannot have residual things that you didn't understand there, and at some time in 2 years' time, someone says, oh, it actually does this bit wrong. So what do? Recall 10 million of them are out there now? Or you go around yourself and change the ROM in every one? What do? You can't afford it. So the skill of engineering is to actually use all the tools and the fundamentals to do totally reliable, high integrity, really honest design. You know this is right. And you've checked it from so many angles and you know it's right. So that's a really important thing to learn about engineering. And when you do a design, all the clever, fancy stuff is this tiny part compared to it's buildable, it's testable, it's maintainable, and everything else. And they're really hard bits to get right. So I can tell you, in those antennas we did, I'll just shoot. In these antennas here, the control system was 100,000 lines of code. It's got some very fancy Kalman filtering algorithms in it. Just took up a few hundred lines out of 100,000. All the rest of it is protecting it, making sure it recandles faults, making sure it doesn't do anything bad to it, all that. All the rest of it. So the really fancy stuff that you spend your time learning about is really important and it really matters, but there's so much more matters in engineering. I would recommend you take a wide interest in everything and read a lot, because all of it ends up helping everything you do. So you should learn to be really great consumers of knowledge. Read different bits of maths, read interesting bits of physics, read bits of social science, read everything you can read. Be hungry for knowledge, it really is important. Do real things, so try and spend some time doing real things. And very importantly, respect the knowledge of other disciplines. You've done 5 years of engineering training or something, but the technician who's done a technician course somewhere knows a lot of really valuable stuff too. And respect it and listen, because actually some things that they understood bits about electricity better than you did. And you'll learn something. So really respect all other disciplines and try and see what you can learn from them and add to it and use it to add to your knowledge. That's also very important. And also, I would strongly recommend you learn a bit about the history of your discipline. So these are people you should know. So this person is Michael Faraday. So all of your electrical engineering started with him in 1821. That's where it started. This person is James Clerk Maxwell, who wrote down Maxwell's equations that do all your electromagnetics, that do everything. And he also wrote a famous paper on control theory that started all of control theory. Because he analysed the governor on steam engines that were going unstable. So he introduced the idea of differential equations to monitor, to do the dynamical systems, and worked out stability criteria. This is William Thomson, Lord Kelvin. In 1850, Lord Kelvin was part of the team that, he did lots of things, in thermodynamics and everything else, and in power systems, but he was part of the team that laid the cable, first undersea cable from England to America, and that cable had incredibly slow data rates. He figured out why, and he so wrote a paper on how you do signalling through that cable at a faster rate. It was like equalisation and signal design for comms. So he started all the signal processing in comms. This is Oliver Heaviside. So all the stuff you learn about the form of Maxwell's equations you use came from this guy, not this guy. He wrote down the div curve forms. And he also introduced operational calculus, which is really what you do when you write S operators in circuits, one on SC, SL, and you analyse circuits. He did it even though it wasn't rigorously founded. Nikola Tesla, who developed the induction motor and had a lot of other inventive stuff, and there were many others in power systems area. Ambrose Fleming, the first person who developed the thermonic valve, and then De Forest in America, he's in England, De Forest in America did the triode, but really he started the idea of the valve, which started electronics. Marconi in wireless. This is Harold Black, who on a ferry going to work from New Jersey across to New York on a bit of paper suddenly realised that feedback stabilises electronic circuits, and you could make electronic circuits that didn't depend on the variation in parameters of resistance. So Black was the first guy who did that, and he really started proper electronics design and control. Harold Nyquist was just a giant in telecommunications, sampling and all that. Then Norbert Wiener, he was a mathematical prodigy. He applied for a job at Melbourne University after he did his PhD in the 1920s in maths, and he had references from the top mathematicians in the world, and he didn't get the job here. This is true, and he got the job at MIT. So Norbert Wiener then became the greatest contributor to mathematics of the generation. And he started cybernetics. He started in artificial intelligence and all the cybernetics movement, all the idea that you can do computers, the communications in the body, all those things he started. But more importantly, he wrote a series of papers. So all the stuff you do about Fourier transforms in circuits, about power spectral densities, all those things, Norbert Wiener did. He was in the maths department. He worked with a guy called Vannevar Bush, who was head of electrical engineering at MIT in the 1930s, and they wrote down all that stuff and took all that maths and turned it into a form where all you electrical engineers do all your systems and circuits and all those things, thanks to Norbert Wiener. And we have a conference next year in honour of Norbert Wiener in the middle of next year down at the conference centre. This is Claude Shannon, who worked out that model of telecommunications. It's a transmitter, a channel, a receiver, and the coding, and then all information theory. But he also worked out all about digital switching. In his master's thesis, he did all the digital switching stuff and building an algebra for digital switching, which you all use. Then in his PhD, and his PhD supervisor was Vannevar Bush, head of electrical engineering at MIT. He did information theory, which revolutionised the world. This is Gilliman. So all the sort of theory of physical systems and circuits, the way we understand circuits, came from Gilliman in the 1940s. And this is Bardeen, Bratton and Shockley who discovered the transistor in 1947 when I was, and that same year my mum was having me. So I'm very fond of what happened in 1947. But that was obviously and there are many others too. But all I'm telling you is you guys live in the heritage of these people and others. But these people are your heritage. This is where electrical engineering came from. It's nice to sort of read about it sometimes and understand it. And you'll be surprised how much stuff they wrote down 100, 150 years ago is exactly what you're doing now, still. And especially if you look at what went on in the 30s in the way we understand physical systems, circuits, analysis of all those things from these guys here, it's identical. So, all right, so that's the end of my talk. So happy to have questions. And there's your pointer. No questions? All happy?
Well, basically what I would like to know is you've done a lot of work on lasers, and I know of the stealth jet that basically evades radar.
Yeah.
Is there something that could be done to be able to track it?
Yeah, there's, so people have lots of ways to be able to do that. So because the radar absorbed material on anything that's not visible by radar works over at certain frequencies, not at all frequencies. So if you move the frequency range, you can usually find things. So there's lots and lots of work done. And a lot of that work, unless you're in the right research centres, which you never hear about, you never know. But there's absorbent material is just a material that doesn't reflect what radio waves at some frequencies. It absorbs it. So at other frequencies it reflects it. Well, you don't know what frequencies, and they would put it at a band of frequencies that most radars work. So if you understand your electromagnetics properly, so study up your Maxwell's equations.
I've heard that it's quite difficult to move between Australia and America in terms of academia because we deal with papers in different ways. Like Australia wants to publish a lot more papers, maybe lower impact, but in America they put more emphasis on.
I don't think that's true. So you know, I've got a lot of papers and a lot of students, and I've worked in both places, and I have collaborated with people all over the world. Everyone wants to write really good papers, everywhere. They just want to write a paper that everyone says this is a great paper, everywhere. Now, the paper counting game that goes on a bit more in Australia is sort of stupid, and people sort of play it to some degree, but it's not the critical thing. The main thing is target good quality journals, write really good papers. That's it. So, but the fact of the matter is, even in the United States, if someone just decides to go for 10 years and not write a paper, and their story is they're working on this great paper, it gets challenging for them. So for the guy who did Fermat's last year at Princeton, 7 years, he didn't write a paper. They nearly kicked him out at the Institute of Princeton. So, you know, they were getting sick of it. So they said, what's he doing? Oh, I'm working on a great paper. Well, everyone can say that. So it's just it's about human relations, really. I mean, obviously, if you're working on something that you think is going to be, and you should try and work on hard problems if you're doing research and try and have things that have impact. But you also got to realise that you can't go through your whole life producing nothing and say, I'm still working on my hard problem. So there's some game that has to be played for people. There's some visible productivity needed. And some places put more emphasis on writing a lot, and some don't. But, you know, everywhere they want high quality above everything else. So I wouldn't worry about that. I just aim at trying to do something. to collaborate with really good people. That's the answer to that. And it's always been the answer. There are only a few people who can just, you look what Albert Einstein did. He couldn't get an academic job. He couldn't get one. But he worked in the patent office, and then he wrote 4 papers in 1 year. One of them started relativity theory, a whole lot. One of them was a key thing in quantum mechanics. One of them started statistical mechanics and Brownian motion. And one of them proved that E equals mc squared and started the whole nuclear industry. 4 papers in 1 year. He hardly had to write anything after that. So, I mean, it's all different, and some people can just churn out thousands of papers, paper every 2 weeks, and it just doesn't matter. None of them matter. So the world's gone a bit mad with publications. It has. The academic world's got a bit mad with publications all over the world in lots of places. But in the end, all the people who know and all the people who matter are only interested in one thing: write some good papers. And if you write lots of ordinary papers, nobody will assess you well compared to writing 1 or 2 good papers. And all the people do the assessment are people like me. I years ago said on the ARC, I do millions of references for people. I assess people to get into the Academy of Science. I don't care if they've written 500 or 50. I just want to find out where's the stuff that proves they're really good. So there are a lot of, it's a lot of sense in the system, more than you think. So don't get panicky about it.
You talked a lot about academics starting companies and directing this. How does that work, and does it ever conflict with your role at university?
Well, so in Australia, they want more of that. So there's a lot of encouragement for that now, and perhaps too much, because the research funding schemes I think they're going to swing very heavily with this government towards work on something that's going to generate jobs, because there seems to be an imperative in Australia that we've lost the car industry, this, that and the other. Where are the jobs coming from? So somehow the academics need to be harnessed into the task of creating jobs, which is bizarre because they play another valuable role. And also these days in Australia, academia is a huge export industry, so because of high quality universities. But and in the United States, there's much more of an understanding and acceptance that academics will have jobs and keep their careers. So in Australia, it's been a bit of a wrestling match over the years, and so what a lot of people sort of do is have to do both. So if you're going to work on in an engineering academic and you're going to work on industrial things, you also have to write the papers that go in the good journals. You have to do both, because there's not an easy recognition mechanism just on the industrial stuff, right? You have to do both. So I think that's slowly changing now. So they're more and more expecting that the academics will actually get involved with industry, either working with companies or starting companies themselves or something. So if you look at Cambridge University now, which was once a very sort of elite, long tradition, Newton was there, and Maxwell used to sit there, etc. Every second academic's got a company now in the Cambridge Industrial Park. So these things change over time, and the universities are moving more and more to encouraging it strongly and wanting you to do it. And so then they change the promotion criteria and they change the assessment criteria to allow it to happen. So it's a dynamic thing. But for you guys, it'll be if you go into academia, I think you'll find it's a really good time to want to do industry engagement and start companies. And as I say, Stan's was here. He's just a serial entrepreneur. He just wants to develop something. He just starts one company after another non-stop, and he does it totally consistent with his academic work and writing papers in Nature. So it's all doable.
What's the best paper you have published?
Well, I think there's a few I'm really proud of, and one I'm really proud of is some of the stuff with Girish and I. Girish is here, one of my PhD students. Some really nice papers that won a big prize for Cyan. It's Industrial Applied Maths. And when in my early years, I published some nice papers in using martingale theory to prove convergence of adaptive filters, certain types of adaptive filters. And I've got some papers with a colleague who died recently, Doko Musiki, but he and I have some papers on target tracking that in the end became the target tracking that everyone around the world uses, etc. So there's 4 or 5 that I think I'm really proud of, the really good stuff. But you know, and you write lots of stuff to go to conferences and you do all sorts of things. And the right time to write some really high impact papers is when you're young. Like, so in your PhD, if you're doing a PhD, you shouldn't panic to write papers in your PhD. I didn't write any papers in my PhD. I went to MIT and wrote some papers, but I didn't write any during my PhD. I was too interested in learning things and doing other things. I did a really good PhD, but I didn't write any papers out of it. Afterwards I did. So I never want to force students to write papers out of a PhD. Unless it's a mechanism where to get the student going, you write a paper and that becomes a chapter, and you write another paper that becomes a chapter. But just the idea that you have to get some papers out the door for a PhD is not necessary at all in my opinion. I'd rather you get quality and write the papers afterwards.
Just wondering what your opinion is on students spending some time in industry before doing a PhD or just going straight from a master's to a PhD.
So for my case, I did work in industry, and I think it was just a terrific experience. And probably at the time I didn't want to do that. I wanted to. And I actually think it's really valuable to do it personally. And a lot of people don't. A lot of people. So what's the trajectory? You know, people are really good at school and they get good marks, they get into uni, and they're really good at uni and doing exams, and then they get into PhD, and they're really, you know, but they're actually, from an engineering academic, you're sort of missing something. You're missing actually what the industrial world's like, and you also don't get to fully appreciate often that problem solving that goes on in industry, and that's what happens in a lot of, like basically there's a problem, you have to solve it, is just as creative, just as hard as doing a PhD. And there's a whole lot of engineers out there who've got PhDs, but gee, they're smart, and gee, they're good at solving real problems. And if you can get in and work with them and learn that problem-solving skill too, some of those problems become great new things for you to work on and research. And some of those problems with industry, they get a practical working solution, but really there's an opportunity to make it a whole lot better if you can put some research time into it. So I strongly believe that the engagement with engineering research seen as a problem-solving thing on real stuff, not as a theoretical exercise on made-up problems, is really important. Because if you're working on made-up problems all the time, you can do theoretical advances, publish papers, but actually they have no actual real translation back into industry or nothing. So I've got a saying about that came from Confucius, is that the name of the thing is not the thing named. I didn't put it up here, but what it means is don't confuse the abstraction with the reality. Work on the reality. You have to abstract it to do maths and things on that reality, because you can't do it on the reality, it's too complicated. But do it in such a way that you understand the difference between it all the time. And you can take that result from the abstraction back into reality. So don't confuse abstraction and reality. And a lot of engineering academics tend to do that, and tend to go floating off into a world of fantasy problem that's actually got no connection with anything. Harsh, but it's true. All done? Anyway, if you want to talk about PhDs or careers anytime, you can always just drop up and see me.
I would like to thank Prof for allocating his valuable time to share his journey in electrical engineering. I'm sure all of you have learned many things from his talk, especially some fascinating stories behind the
behalf of the IEEE